To the club. All right, so for number 4 here, we're looking at 3 secant x over 2 minus 1. All right, so we can handle this. I mean, we've been doing it all by hand. So, I mean, that's just something to keep in mind in terms of the fact that we do it by hand, but you also have a calculator at your disposal. All right, the thing is, the calculator, in terms of a table of values, does not think in terms of pi. So that could be kind of an issue, but you can at least use it to check your work. So the standard form for a secant function, a secant bx plus c plus d. All right. Now, just like we did with the with example number 3, we have to take into account where the asymptotes would be. All right. So it is the reciprocal of cosine. So wherever the cosine function is equal to 0, the secant function is going to be undefined. All right. So there's a couple of ways that you can handle that. What some people will do is they'll go to the calculator just for the asymptotes and then, just build the rest of the function from there. What I mentioned last time is that what we should do, if you're doing it strictly by hand, is you treat it as if it's the cosine function. So you find your a, b, c, and d values. All right, so 3. The b value would be 1/2 because this is the same as saying 1/2 x. There's no other loose term in the parentheses aside for the x over 2. So c is going to be 0 and d is going to be the -1. All right, so that would be corresponding with, the loose term at the end. All right, so the amplitude is going to be 3. The period, 2 pi over b. That's 2 pi over 1/2, which is 4 pi. Phase shift, we're not worried about. The vertical translation, VT, is -1. All right, so we have the ingredients. If this were actually a cosine function, we have the ingredients necessary to plot it. All right. So now I need to go from -pi to 2 pi, and I have to also be prepared to shift it up and down. So my amplitude is 3, and I need to shift down 1 unit from there. All right, so labeling the vertical axis should be okay. We could just go by ones. Start off with that, and I'll add more increments if I need it. And then for the horizontal one, since there is no phase shift, no horizontal shift, I can pretty much decide on whatever I want to be equal to pi. All right, but the period is 4 pi. We're not going to actually go out to 4 pi, but there could be an instance where you would need to graph the entire period. Like if this said going from -4 pi to 4 pi, so in those instances, you'd probably want to keep your pi closer to the y-axis. Here, it doesn't really make a difference. All right, so I'm going to let 6 units equal pi. Remember, you could do any even number of increments. So pi, 2 pi, 1, 2, 3, 4, 5, 6, and -pi over here. All right. Now, the cosine wave starts off at its maximum, then hits the midline at the quarter-wave point, then it hits the minimum at the halfway point, and then, back to the midline, back to the max. All right. One way to handle that would be to take your period and multiply it by 1/4, 1/2, 3/4, and 1. All right, so 4 pi multiplied by each of these. So 4 pi times a quarter is pi, times a half is 2 pi, times 3/4 is 3 pi, and times 1 would be 4 pi. All right. Now our domain caps off at 2 pi. So that's the farthest we'd have to go. All right. And remember, for a cosine wave, it's high, middle, low, middle, high. So max, midline, min, sorry. You start at the max, the quarter wave point is the midline, then the min, then back to the midline, and then back to the max. All right, so technically, this maximum here would be what you get if you took 4 pi, multiplied it by 0, right? But I'm just going to say that this is going to be at the y-axis. All right, so at the y-axis, I'm at my maximum. At pi, I'm at the midline, and at 2 pi, I'm at the minimum. So I can do a little dashed curve there. Then I could also go the other way. It's going to put me at negative pi. So this would be an untranslated cosine function. Now we need the secant, so I need the reciprocal of this. All right. But what I want to do is figure out where the secant function would be undefined. Right? It's undefined whenever cosine is equal to 0. All right. So what I could do, I can take, let me just get rid of this for a minute. I could take my secant expression, just this little piece here, and instead of looking at secant, I would look at cosine of x over 2. Now, if you want to, you could actually do it using using the reciprocal function, because secant is the same as 1 over cosine. All right, 1 over cosine x over 2. Now I want to know where that would be undefined. Right, it's undefined, giving a vertical asymptote or a set of vertical asymptotes, or being undefined gives it that. All right, so I want to know where, let me get a lighter color here. We'll do that, where this is equal to 0. All right, now what we just did, we graphed the cosine function. And so I'm just kind of re-explaining what I talked about last class, because I know it's been a couple weeks. All right. So what we just graphed, that dashed curve, that is y equals 3 cosine x over 2. All right. Now, if I wanted to take this whole expression, including the 3, then this would become 3 over. But that 3 doesn't have any bearing on this whole thing, because I still need to know where it's undefined. So that's why I only focus on the cosine part, or the secant part of it, making that into 1 over cosine. So I'm just looking at cosine instances where cosine is equal to 0. All right. Now you could do it in your calculator. You can create a table of values if you want, but we already have that information. All right. Cosine is equal to 0 whenever this graph touches the x-axis. All right, so cosine is equal to 0 here and here. And if we had more domain to work with, it would be, there'd be more values, but we don't, so there aren't. All right, I'm just going to move that over there. All right, because I'm going to create, what color did I use last time? I did use green. Okay, so I'm going to create vertical asymptotes here. All right. Now, everywhere, or in every interval, I should say, there's going to be some part of the graph, all right, bounded by the vertical asymptotes. So what I'm going to do is I'm going to shift up every point on my cosine function I'm going to shift it up. I'll use different color here. I'll use red. Every point gets shifted. Oh, sorry, shifted down, because that vertical translation, the D value, is -1. So I'm going to shift every point down 1 unit. Draw another intermediate graph because it's still not the secant graph. But now I'm going to flip each part. All right, so this part here opens down. So I want the real graph to go through that vertex, but open up. All right, this part here opens up. So going through this vertex here, I want it to open down. So it's just going in the opposite direction. My shaky handwriting is in full effect. All right, so that would be the secant graph here. Now, like I said before, you could do it on a calculator, but you sort of have to learn how to speak in terms of pi. All right, so let me just show you real quick. I'm going to go to Grapher. I have the one from last time in, right? But I'm going to kind of show you from scratch. So add an element, y equals or f of x equals, doesn't matter. They're both functions, or the what you're given will be a function. So I want 3 secant. All right, so to get the secant function, we have to go in the trigonometry menu. Advanced, and then secant. All right, so again, oh, actually, I didn't want to do that. 3. So you go toolbox and bring it back to the beginning here. They kind of did it a little too quick. All right, so you're in your toolbox. You scroll down until you find trigonometry. Hit OK. Go to advanced. Hit OK again, and now you have all the good stuff. All right. So all the stuff that's not on your main keypad. So I need secant. And I want to put in x over 2. So x divided by 2. And then -1. I'll hit OK to lock it in. Now in the upper left-hand corner of your display, you see rad, right? So it's in radians, and we want it to be in radians. So that's good. I can go to graph to look at the picture, but as we know from previous experience, sometimes that that window isn't user-friendly. So we'll give it a look, but I don't have, well, I was going to say I don't have high hopes. It actually doesn't look half bad, right? It's way beyond what we need, though. You see, it goes up to 12. So I change my axes. I want my x-axis to go from a minimum of -pi to a maximum of 2 pi. All right. And then my values of y, well, I definitely don't want it to go all the way down to -26. All right. So maybe I'll do like -10 to 10. I want to give myself some space, but I don't want to go too crazy. So confirm. And, you know, this is a nicer version of what we have on paper, but it's the same. It looks like it goes through the y-axis at 2 units above. And it looks like it gets to 2 pi. So the rightmost point there at -4, 4 units below the x-axis, which is what we have. All right. You could also look in the table. All right. So this is in increments of pi. If I want to get that -pi in here, I want to do set the interval and make my x start -pi. Now we have it going in increments where it says step. It's increments of pi. So that happens to align with what we want here, but it won't always. So you might want to change that from time to time. So confirm. And now what it's saying, let's see here. Well, it's saying something that's not correct. So that last point, the negative 3.14, the negative pi, it's giving a pretty extreme value. And it's fine, I guess, but it's on a boundary that is an asymptote. All right. So we're kind of running into the issue here that it's telling us that at negative pi, we should plot a point that's like almost 10 units below the x-axis. Right. That's not what we had on paper. All right. What we had on paper was something that's opening upward. Right. So 0, 2 fits. That's fine. Right. That's the y-intercept. At 2 pi, we have a negative 4. That fits. But it's given us something really funky around the asymptotes. All right. So, the the graph matched what we had, but the graph, the table itself isn't really telling the correct story. All right. So that could be a little frustrating. In fact, what's happening is that point, it must be it's an approximation of pi, but it must be on the high side, or I'm sorry, on the low side. So at some point over here, what it's saying is that there's a point like really, really close to pi, like just a smidge to the left of it, that's like here-ish. All right. So if we created more of this graph, there would be another part of it that went like this. All right. So it's just that's not included in the domain, but the calculator's giving it to you anyway. So you just got to be cautious about that. All right. So that is reciprocal trig functions. We also have other types of trig functions like tangent and cotangent functions. The tangent function is a little bit easier. The cotangent function, well, it's related closely to the tangent function. So if you understand one, you understand the other. All right. It's kind of alarming when you look at a graph like this and say, how am I supposed to come up with that? But the key here for tangent or cotangent is getting those vertical asymptotes, right? So it's actually more aligned with reciprocal functions than you might first suspect or realize. I'll just do it with a thinner one. All right. Tangent functions and cotangent functions are also periodic, which means that they cycle repeatedly. So if you can come up with the asymptotes over whatever domain you're working with, then the rest is really kind of easy. All right. So that's all I'm saying here. All right. So I just kind of like mumbled my way through that explanation. But let me take you through the first couple of examples here. Y is equal to a tangent of x. All right. So if you want to create the graph, like I said before, in NumWorks, you can. I'll just clear it. Okay. Y equals tan x. And then you look at the graph and you get something like that. And you're like, okay, so I have to get this on paper. Right. Now, I still need to establish, they didn't give us a domain, so I still need to establish where pi would be. All right. But before I do that, I want to figure out where this graph is undefined. All right. So tangent is equal to sine over cosine. All right. So I could actually start off by making a cosine graph and then use that to help me make the asymptotes and then the tangent function. But it's going to get really messy. I mean, if you thought the secant, cosecant ones were messy, that this is going to, it'll be beyond. Let's just say that. All right. So we're going to use a more analytic approach. So I'm going to say, again, where is cosine x equal to 0? couple ways to handle it. One would actually still be involving a cosine graph, except on the calculator as opposed to by hand. Another way is to use an inverse function. All right, so take the inverse of both sides of the equation and you'll get your answer. But the preferred way is using a unit circle. All right, so on the unit circle, and I'm just going to do the shell of it. I'm not going to do the entire unit circle in its full glory because we don't need most of it. Just get a circle here. Make it halfway decent. All right, around the unit circle, we have points 1, 0, 0, 1, negative 1, 0, 0, negative 1. In the unit circle, x, y corresponds to cosine theta, sine theta. All right. So coordinates x, y correspond to cosine theta, sine theta. Here we're in this problem, we're using x as the independent variable, but we're really treating it like a theta. All right. So we're going to treat it like theta. All right. So around the unit circle, we have angular measures. This one would be 0 radians. This one is pi over 2. This one's pi. And this is 3 pi over 2. All right. So the ones that have 0 as their x value, those are going to be the ones. Those will be the, oh, that's not really much of a highlighter. Those will be the relevant ones. All right. All right, so cosine is equal to 0 at pi over 2 and 3 pi over 2, among other places, but that's enough to get us going. All right, so I'm going to create my scale on the horizontal axis. Vertical axis, we could just go by 1, so we'll leave that alone. All right, I'm going to let 4 units be equal to pi. Here's pi. 2 pi, go the other way. They didn't give us a domain, so we'll just do the standard negative 2 pi to 2 pi. And if there's a little extra on the sides, we'll include that too. There will be. All right. So I need a vertical asymptote at pi over 2. All right. Pi over 2 is right here. So vertical asymptote there. All right. And I also need one at 3 pi over 2. So it's going to be over here. There's really no good place to put it, so I'll just leave it right there. All right. And what that tells me is that according to this scale, every 4 boxes, there should be an asymptote. All right. So if I go 4 more boxes to the right, I'll have a vertical asymptote. 4 boxes to the left, another 4 boxes to the left. More and more vertical asymptotes. All right. So then it's a matter of just plotting the curve. So a tangent function is always going to be symmetric about its midline intercept. All right. So we treat the tangent function like we would any other function of a trig variety. It's y equals a tangent bx plus c plus d, right? So we would still get things like period, phase shift, vertical translation, and stuff like that. And also an amplitude, but the amplitude doesn't have as much of a noticeable impact when you sketch it by hand as it does for other types of functions. So what I'm concerned with is whether or not there's a vertical translation, and there isn't. Let me show you really quickly. I'm going to go back to expression. If I took this function and added a 3 to it, for example, same graph, just shifted 3 units up. All right. So it really does work in that fashion, the same way as in a sine or cosine function. So I did down, -4. It got shifted down 4 units. Just fix it. All right. So wherever the midline is, and if there is no vertical shift, then the midline is the x-axis. Wherever that midline is, at the midpoint between vertical asymptotes, you're going to have a point. You're going to plot a point. Let me get something that stands out a little bit. So each one of these will have a point. All right. Now, if you want, you could also look at the numerator of the function, y is equal to sine x over cosine x. Just like wherever the bottom was equal to 0, it was vertical asymptote. Wherever the top is equal to 0 is where the x-intercept would be. All right. The thing is, if there's a vertical translation, the x-intercept would not be the point you're really looking for, but it could be helpful along the way. All right. Now, this graph is going to approach both asymptotes, but in different directions. So we start low and end high. And we just do that repeatedly. All right, and so this would be my tangent graph. It's a little skinnier than what you see on the numworks, but that's because I have it going on numworks from like -8 to 9. I'm going -10 to 10 on this one. If I adjust the window, it might look a little closer. It doesn't have to be perfect though, because we're really just estimating. All right. And so it's just a rough sketch. Kind of like when we were doing polynomial functions. Right? You just want to know where the important points are and the general shape. Shape being the first word of the day. Shape. Like as in a square is a shape. All right. Or this is shaping up to be one heck of a lesson. Shape. All right. So the next one is tangent of 2x. So that's the same as saying y is equal to the sine of 2x over the cosine of 2x. This one's a little trickier because what I need to figure out is where cosine of 2x is equal to 0. All right. So, and that'll help me get my asymptotes. So I'm going to say, where is cosine of 2x equal to 0? All right. There's like a little nifty trick though. If I'll use theta. I'll let theta equal 2x. Then I'm really asking, where is cosine of theta equal to 0? And you're like, okay, well, clever trick. How does that help? Well, the unit circle tells us where cosine of theta is equal to 0. Right? At pi over 2 and 3 pi over 2. So theta would be equal to pi over 2, and theta would be equal to 3 pi over 2. Right? Now, if it were that simple, then, like there wouldn't really be much of a topic of study. What we now need to do, since we made theta equal to 2x, let me go with like an orange here. We let theta equal 2x, and now I know theta is equal to pi over 2. That means 2x is equal to pi over 2. It means 2x is equal to 3 pi over 2. All right, so it's kind of like a little clever workaround so that you don't have to create the entire graph of a cosine function just to see where it crosses the x-axis. All right, when I solve, I get x equal to pi over 4, and x is equal to 3 pi over 4. So a little bit of extra work, but nothing too crazy. Now, a shortcut to the shortcut would be, if you know that in the unit circle, cosine is equal to 0 at pi over 2 and 3 pi over 2, then all you'd need to do is divide those numbers by whatever the coefficient of x is. Right? So for example, if I had cosine of 6x is equal to 0, x would be equal to pi over 2 divided by 6, and x would be equal to pi over 2, 3 pi over 2 divided by 6. So pi over 12 and 3 pi over 12. All right, so the one clever method is good, but sometimes you just want the numbers really quickly, so you could do it that way. The issue, well, it's not really an issue, it's just a caution. I know some people are like, well, I'm just gonna do it on the calculator. I don't know that you're gonna necessarily be able to look at a decimal and say, well, that smells an awful lot like pi over 12. You're gonna look at a funky decimal and be like, that's a funky decimal, right? So just be careful about over reliance on the calculator. All right, so I'll just box this. Oh, I lost it. I guess when I went off the edge there. All right, that's just a side example. It's not related to this problem. All right, but I do need pi over 4 and 3 pi over 4. So if I'm going with the scale that I had before, with pi being equal to 4 units, so same setup. Pi over 4 would be a quarter of the way to pi, right? Because remember, pi over 4 is the same as 1/4 of pi. 3 pi over 4 is 3/4 of pi. All right, so if the distance from 0 to pi is 4 units, a quarter of that would be pi over 4. And 3/4 of that, or 3 boxes, would be 3 pi over 4. Still no vertical shift. So that's good news, because that means that we know a point on the midline that's going to be directly in between each of the asymptotes. I need all possible asymptotes though, so I'm going to populate or propagate. Fill in any gaps that might. So every 2 boxes. Oh, I took the, okay, I'll fix that in a sec. Let me clean this up. All right, and I need another jammy in there. And I also need to go a couple more. All right, well, one more in either direction. Let me do that. All right, so we'll start off at the origin and work our way out. So I'm going to have a point here, and the graph is going to approach the vertical asymptote on the right, on the left, as it goes downward, and it's going to approach it to the right as it goes upwards. All right, so I need all of these. And it's not going to be perfect, but you just do the best you can. Now, there is a little extra bit of domain here. So I can put my graph in, but some of it's going to go off the page. So I'll get rid of that. I don't need that. We run out of room right here. And that's going to happen on the other side also. Get there in a sec. And one more. So you see it goes off the page, but on the low side. So get rid of all the stuff we don't need. And we get a point there. All right, and we'll get some arrowheads on the bottom here. Although it's so compressed now that it's hard to tell if they're even there or not, or whether they are there or not. All right, but that is the tangent of 2x function. And again, in your calculator, put in a 2 in front of the x, graph it. You see there's more of them. All right, if we want to change our axes, we'll go negative 2 pi to 2 pi. I'll leave the y's alone, confirm. I mean, again, it's nicer on the calculator, but it looks like we have the appropriate number of pieces and half pieces, right? So you get a good sense of what the output of the graph should be just based off of the calculator. But then, you go through the process. Now, sometimes it's possible. I mean, I would say more often than not, academically, you would be looking at instances where from the graph, you could probably easily pick out certain points, and that might be enough for you to get what you need, right? Let me actually show you what I'm talking about here. So if I go to, I think it's navigate. No, navigate's not the right one. Well, just hitting left and right. At 0, it tells me the coordinates are 0, 0. So I mean, at the y-axis, it tells me the coordinates are 0, 0. If I continue, my next x-intercept is at 1.57. All right. So if maybe you don't recognize that, but 1.57 is half of pi. So that would be at pi over 2. All right. But maybe you continue. This one's a little bit more obvious. There is an x-intercept at 3.14-ish, so at pi, right? And this other point here, I'll just kind of scroll back to it. This point here looks like it's about half the distance between 0 and the one at pi. So maybe you can infer that it's pi over 2. All right. Sorry, I'm just straightening this out a little bit. It kind of jumps on me. I want it to kind of stay rough. That's fine. I can live with that. Yeah, I wanted it to stay kind of roughly centered. But yeah, there's plenty of ways that you can use the calculator as a tool to help you, kind of grease the skids a little bit. All right. Now, a cotangent graph. All right. So it's the complement of tangent. So I mean, you could use that information, but it's also, so we'll look at it a couple of different ways. Cotangent of theta is the complement of tangent of theta, right? But you could also look at cotangent of theta being the reciprocal of tangent of theta, which means that instead of being sine over cosine, it's cosine over sine. So the long story short with cotangent is we're going to do pretty much the same stuff we did for the tangent graph. We're just going to do it from the perspective of sine. All right, so now I'm not looking for where cosine is undefined. I'm looking for where sine is undefined. Oh, well, sine is equal to 0, I should say. Let me grab this. Because I know I'm going to need it in a minute. So when I look at the cotangent of x, again, y is equal to cosine of x over the sine of x. We would want to be finding where sine is equal to 0. So I'm going to make a little edit here, stealth edit. All right. So the x in the function, again, we're going to treat like a theta. We're looking for where sine is equal to 0, sine of x. And that would be any instance where the y value is equal to 0. All right, so the y value is equal to 0 here at 0 and here at pi. I almost had it. It's probably good enough. Get rid of some of the fluff here. Good enough. I lost my fraction bar though. So the orange highlight. Right, so that's at 0 and pi. So I'll set up my axes the same way I did before, putting the pi here, 1, 2, 3, 4, putting 2 pi here, 1, 2, 3, 4, negative pi, 1, 2, 3, 4, negative 2 pi. So at 0, I'm going to get a thicker pen. At 0, I'm going to have a vertical asymptote. And I'm also going to have one at pi. Right, so the vertical asymptotes are separated by 4 units. And because it's periodic, that means every 4 units, there should be another vertical asymptote. So I'll have one here. Here. And lastly, here. All right, just like the tangent function, on the midline at the midpoint between the 2 vertical asymptotes, there will be a point on the graph. The difference between tangent and cotangent graphically is where tangent starts low and ends high, cotangent starts high and ends low. And the reason for that, and I'll actually just show you the intermediate graph. So I'll just do it real quick. This is what the tangent would look like. So this would be part of the tangent graph. Just like we did with the reciprocal functions cosecant and secant, the part that opens down should now open up. Right, so it opened down previously, so it should now open up. the part that opened up previously should now open down. All right. So that's the justification for it. It's a flip-flop. It's like a reflection. It is a reflection. So just like this. Copy, paste, 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 and paste. All right, so just like with the tangent, part of it went off the grid. So I cap this one here. And I would end this one here. And I just get some arrowheads on it and we're good. Just wanted to make sure I had some funkier examples because I didn't want to, what you call it, yeah, I didn't want to just leave, you know, classic teacher move, do all the easy ones and then leave the hard ones for you to figure out, and try to avoid that kind of thing. With that in mind, we're going to skip number 2 for now. I'll put a star on it. We'll come back to that on Wednesday. Right, because I want to, you know, like I've been doing throughout the course, like to leave some of the material from one class to be covered the following class, so it serves as like a bridge, little review. All right, but let's take a look at number 3 now. A couple of things going on with this one. Sorry, I just got something caught in my throat there. A couple of things going on. One, the A value is negative. And the other thing is that the B value is something other than 1, right? So we got to account for that. So just like sine, cosine, secant, cosecant, and cotangent, we have a standard form. Secant, cosecant, and tangent is what I meant to say. We have a standard form for this type of function. The standard form is the same. It's just cotangent instead of cosine or sine, you know, so like there's some familiarity in that. All right, so the A value is -1. All right, if the A value is negative, we're going to reflect over the x-axis. Quick example. And we've talked about this already, but I'll do it again because again, it's been a while. So let's say I have sine of x. And I have, oops, that's not what I wanted. Oh, yes, it is what I wanted. Negative sine of x. All right. The regular sine function is in blue. The other color is for the negative sine function. You can see that they're reflections over the x-axis of each other. All right. Other being the second word of the day. Other. As in they're reflections of each other. All right. Or this is the, that was going to be a crappy sentence. I'm trying to come up with one that involves other that doesn't involve another. All right. So, do you want these shoes or the other shoes? Yeah. Something. Right. So reflect over the y-axis. We'll keep that in mind. We don't have to do that right away. Right. I do need the B value. Right. The B value is equal to 1/2. All right. Now, this cotangent function is still thought of as cosine over sine. So I could rewrite this as y is equal to negative cosine of 1/2 x over sine of 1/2 x. I could put the negative on the top or the bottom, or I could just put it out in front if I want. Doesn't make a difference. Doesn't really have much bearing on the calculations that we're going to do, but it does in terms of the overall shape of the figure. All right. So again, I want to know, where is sine of 1/2 x equal to 0? And again, we're doing this because we know that the bottom of a fraction, if it has a variable in it, could lead to the fraction being undefined. If it's undefined, it's because there is a location in which the denominator is equal to 0. So we'd have to figure that out, right? Now, most of the time, an undefined fraction leads to a vertical asymptote. In the case of reciprocal functions, it certainly does. All right, so I'm going to use a trick from before. I'm going to let theta equal 1/2 of x. So I'm asking myself, where is sine of theta equal to 0? That would be at 0 and pi. Figured that out before. So if theta is equal to 1/2 x, then 1/2 x is equal to 0, 1/2 x is equal to pi. So x is equal to 0, and x would be equal to 2 pi. All right. So might be wondering why I identified the b value. All right, where I said b is equal to 1/2. Well, that's going to give us the extent of, it's the period of one full tangent cycle, I guess. So if I say, for example, tangent of just y is equal, cotangent of x, tangent of x, it has the same structure. If I say that y is equal to the tangent of x, that's a period of 2 pi. That means you're getting all of the tangent function, one complete cycle between 0 and 2 pi, right? Now, in this case, the period 2 pi over b, 2 pi over 1/2 is equal to 4 pi. All right, so the tangent or cotangent function would have a complete cycle every 4 pi radians, right? It gives me a sense of what the size of the figure is, all right? So this is going to be double the width of an ordinary cotangent function. So if you go back to what we did here and just double the width, then you'd pretty much have it, all right? So I'm going to go the same scale, pi, 2 pi, negative pi, negative 2 pi. Previously, I had my vertical asymptotes at 0, pi, 2 pi. All right. So now my vertical asymptotes are going to be double the width. So 0 and 2 pi. All right. So knowledge of the parent cotangent function could help you with transformed functions. Because you'd say, well, how does this relate to the parent function? It's double the width. Okay, so if I have asymptotes every pi over 2 units, for example, then I would double that. You know, in this case, it would be every pi unit, so I double it. So 0 and 2 pi instead of 0 and pi. All right, same relationship in terms of where the x-axis intercept comes into play. Now, the big difference here is that it's negative, right? So if I were to create this graph, this would be the cotangent function as if assuming it were positive. I'll do it as a dashed. All right, so this is equivalent to y equals cotangent of 1/2 x. All right, that's that blue dash curve. I want negative that. So let me get a bright green, something that kind of pops. So I want this graph. All right. Now we do have some extra domain here. So I would just want to get a sense of what's going on. I'm going to be looking at something that goes off the grid, right? Because it's never going to quite get to the x-intercept, because that would require it to go out a total of 4 units from this vertical asymptote. It only goes out 2. So it's going to get part of the way, but then it's going to cut off. Oops. And you just estimate a point there. Doesn't have to be perfect. All right. And this one, same deal. It's going to get cut off at the edge of the grid. And you're going to have some floating point over here. All right. So let's take a look at the graph. This was cotangent, but I'm sorry, negative cotangent, toolbox, cotangent, 1/2 x. And then just for giggles, I'm going to put in tangent 1/2 x. All right, so the cotangent should be that bluish color, the negative cotangent, and the other color would be tangent. All right, so you see that they have the same shape, just the tangent function is translated. All right, so when you flip a cotangent function, all right, when you flip a cotangent function, it ends up being some kind of tangent function. All right, there is an equivalent tangent function out there for every cotangent function. All right, the fact that this is negative flips it back to the same orientation as a tangent, but it is still going to be shifted based off of the fact that tangent has cosine in its denominator. So any instance in which cosine is equal to 0 would be a vertical asymptote. And the cotangent has sine as its denominator. So any instance in which sine is equal to 0 would create as vertical asymptotes. So if for ordinary parent function, that would be a 90-degree shift, or pi/2 shift from one function to the other. That I could show you also real quick. So if I made this negative cotangent, but just of x, versus tangent of just x, create the graph. It might be hard to see, but one of them is shifted pi/2 units from the other. And in fact, I can create a shift by adding or subtracting pi/2 from the x value in the tangent function. So I'm going to do just x minus pi/2. All right, so now they're the same function. So one of the powerful things about trig is generally, if you know one function, all right, literally one trig function, everything there is to know about that trig function, then you can deduce the other 5 trig functions from your knowledge of that first one. All right. That first one being sine. So if you know everything there is to know about sine, then it's only a matter of time before you can express knowledge of everything else. All right. Let me do a tangent with all the bells and whistles. So number 6, I'm going to put stars on 4 and 5. And we'll come back to those. next class. All right, so this has got all the good stuff. Again, I care where this function is going to be undefined. So I'm going to pull this out and look at it. It's going to be the same as saying sine of 2x minus pi over 4 over cosine of 2x minus pi over 4. I want to know where this is going to be equal to 0. All right, so I'm going to let theta equal 2x minus pi over 4. All right, it's a little bit more complicated, but essentially doing the same thing. So where is cosine of theta equal to 0? When theta is equal to pi over 2, or theta is equal to 3 pi over 2. Since theta is equal to 2x minus pi over 4, we would say 2x minus pi over 4 is equal to pi over 2, and 2x minus 4 pi over 4 is equal to 3 pi over 2. Let me just a little bit, create a little more space. So 2x minus pi over 4 is equal to 3 pi over 2. All right. So I'm going to solve for the value of x. I'm going to add pi over 4 to both sides. All right. So 2x pi over 2 is the same as 1/2 pi. Pi over 4 is the same as 1/4 pi. A half plus a quarter is 3/4. So 3 pi over 4. Three pi over 2 is 1.5 pi. Pi over 4 is still 1/4 pi or 0.25 pi. If you put them together, you get 1.75 pi. Maybe you don't want to do it that way. What you could do is in your calculation menu, when you're combining these terms, ignore the pi's. Pretend the pi's aren't there. So I would say 3 over 2 plus 1/4. And you get 7 over 4. You just got to bring the pi back to the party. So then I'm going to divide both sides by 2. All right, so it's going to be 3 pi over 8 and 7 pi over 8. All right, so what I need here, now this takes into account pretty much everything except for the vertical translation, which is good. All right, it's taking care of the phase shift, because by knowing where the vertical asymptotes are, I really know where the graph is, because the graph has to live between the two vertical asymptotes. All right, I just need to know what the midline is in order to create a midline intercept. All right, so this is a vertical translation. VT is equal to 1. All right, so I'm going to create a new midline here. Let me do it like this, and then I'll erase to make it dashed. All right, so this is my new midline. All right, so you're going to treat it like you would the x-axis. Treat as x-axis. All right. Now for my vertical asymptotes, 1/8 of a unit is kind of tricky. If I don't have the right increments, I could find myself doing a lot of estimation, right? But what I could do is let pi be equal to 8 units. All right. So because they didn't give me a domain, I have liberty to do pretty much whatever I want as long as I demonstrate the cycle. All right. So if I let pi be equal to 8 units, that's going to take up most of the graph. Now, the period, and I'll just kind of chuck this off on the side. It's like what I did before with the period. It gives me a sense of what I should be expecting to happen. The b value is equal to 2. So the period is 2 pi over b. So 2 pi over 2 is equal to pi. And what that tells me is I get everything I need in terms of the attributes of the tangent function between 0 and pi. All right, so I actually am okay going from negative pi to pi because I should get an entire tangent wave in that period anyway. All right, so now coming up with 3/8, well, they're 1/8 units. So 3 of those 1/8 units put you right here. And then the other one was 7/8. So that's 1, 2, 3, 4 to the right, or 1 short of pi, which would be 8 over 8. So I now know that every 4 units, I'll have a vertical asymptote. All right, so 1, 2, 3, 4. So it's not symmetric about the y-axis anymore, but it will have symmetry within the asymptotes. All right, so I know that I'm going to have, let me go green again. I know I'm going to have a point on the midline halfway between the asymptotes. So that's here, 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 here. I can get one here, and the other one will be off the grid. All right. I know it's going to start low and end high because it's a positive tangent function. That amplitude, the A value, that talks about the steepness of the tangent function. All right. Now, since we're doing rough sketches, like ordinary tangent function is going to look pretty much the same as a 2 tangent or a 5 tangent. All right. It's going to get very steep very quick anyway. So we could sort of ignore that. All right. And just draw the tangent function the way we normally would. And propagate throughout the domain. And again, this is an unrestricted domain. So that means that we can go on forever and ever, which translates to academically, we want to use every bit of grid that we have available to us. All right, so parts of it will go off the grid. We ignore those. Get some arrowheads. The parts that go off the grid, you don't put arrows on that. All right, same deal here. You wouldn't put an arrow there because you'd have to actually complete the full cycle before you could put an arrow. All right, so you just leave those without arrows. And that would be my amped up tangent function. All right, so that's got a lot going on. This is the kind of problem where you're like, up until this point, you might be like, I'm not going to touch the calculator. I'll just do it. I'll do it using the process. But this one, you kind of want to take a look at it, only because you do all this work. You want to make sure that you didn't just botch it. So 2 tangent 2x minus pi over 4. Plus 1. All right, so it looks like I have it in the way I want it. Go to graph. and you see, it's not exactly a duplicate, but it's pretty close. I mean, if you look at -6, -6 is right by -2 pi, right? This one goes out a little bit further. So this is pretty spot on what you see on the display. It's pretty spot on to what we have on paper, right? So we're in pretty good shape. And you can see if I put y equals 1, I'll just do that real quick. And let's see, I'll do it as a I don't know, something that looks halfway decent. I guess orange is fine. And yeah, I think that's good. Plot restriction, fine. Yeah, that should be okay. Yeah, it stands out pretty good. So if I scroll up, it does look like the curve has its point of symmetry right on, or each part of the curve has its point of symmetry right on the orange line, right? So it's, again, the calculator can be kind of spotty when it comes to getting information to create a graph, but it's pretty good in helping you verify that the graph you just created is correct. All right. So yeah. Let's see, time. Just want to do one last thing. It should only take a few minutes. I wanted to at least get us started on inverse trig functions. Right. So it's really just talking about one full cycle of a cosine wave and how that relates to an inverse trig function. Little issue with, oops, not moved on me, with the notation here. It's just weird the way it came out. This should be y equals the arc cosine of x. I'm just going to very quickly do a cosine function on the domain of 0 to 2 pi. Here's 2 pi. I'm going to call this 1 here and this -1, just to use a little bit more of the graph. All right, the cosine wave starts off at its maximum. And I don't know why I didn't put the 2 there, sorry. At the quarter wave point, it hits the midline, then the minimum, then the midline, and back to the maximum. All right, so this is one full cycle of a cosine function, cosine curve, cosine wave. Now I'm going to label up the points, the actual coordinates. This one's 0. Oh, that's a little too thin. This is 0, 1. This point here is pi over 2, comma 0, pi, comma -1, and 2 pi, comma 1. All right. So I put a couple of recall statements up here. So I say recall, to find the inverse of a function, you switch the x's with the y's. Domain becomes range becomes the domain. The inverse of a function may not itself be a function. All right, all that stuff is helpful, but we're just going to focus on the first one, which is to find the inverse, switch the x's and y's. So that's what I'm going to do. I'm going to take each x value and switch it with the y value. All right. So 0, 1 is going to become 1, 0, for example. All right. So 1, 0, by creating a scale similar to what I have on the other one, I'll put -1 here, +1 there. 1, 0 would be right at this location here. All right. Then we'd switch these two. So we'd have 0, comma pi over 2. All right. So pi over 2 is half the distance to pi. So that would put me right here. All right. Switching these two, -1, comma pi would put me right here. So I can connect these curves, connect these points into a smooth curve. Now, if I plot any more, well, one, I'm going to go off the grid, but that's not the real reason. The real reason is I've already covered the domain. I've already gone from -1 to 1. So any other points that I might include would cause the graph to be undefined. Sorry, not a function. All right. So for example, this next point here, which I neglected to write, this point here would be 3 pi over 2, comma 0. If I plot 0, comma 3 pi over 2 over here, that would cause it would cause it not to be a function. I'd fail the vertical line test. I'd have more than one intersection with a vertical line. All right. Oh, I don't know what just happened. So I don't want that. So I would just stop here. All right. So what that tells me is that the arc cosine function can only exist between y values of 0 and pi. All right, because anything beyond that would cause it to fail the vertical line test. Like if I did this, fails the vertical line test. All right. That being said, this is one of the few functions where you pretty much get everything you need from the calculator. I don't think that's anyone. You can just double check, make sure my wife isn't trying to call me. Nope. Okay. Telemarketer. So spam call, whatever they call it now. Y equals arc cosine, so shift cosine of x, pop it in, and that's your graph. If I try to navigate along the point, or I'm sorry, the graph, it breaks at this location. It'll only go as far as 1 before it just ceases to exist. It'll only go as far as -1 before it ceases to exist. All right. So those are the points. And if you go to the table, you can see you have a point at 0, pi over 2, and anything beyond 1 or -1 is going to be non-real. All right. So what I would do here is I'd set my interval to -1 to, that's not a -1, -1 to 1, going by ones, confirm. At -1, we have a pi. At 0, we have a pi over 2. And at 1, we have a 0. Connect it with a smooth curve, and you have it. The same is true for the arc sine. So if I do an ordinary sine function, here's pi over 2, negative pi over 2. I'm going to do this one from negative pi to pi. The sine wave starts off at the midline, increases to the maximum at the quarter wave point, then back to the midline at the halfway point. I'm at a domain on the right side, so I'll go the other way. So high, down to middle, low, then back to middle. So this is what the sine wave looks like over the interval of negative pi to pi. Same idea, you just start grabbing some points. I'll start with 0. first coordinate 0, 0. Even if I swap those values, that's nice and easy. Still 0, 0. Then I'd have pi over 2. I'm sorry, this is, oh, I don't know why I wrote this. That was foolish. Sorry about that. This should be pi over 2. Pi over 2, comma 1 becomes 1 comma pi over 2. So I'll call this 1 and this -1. So 1 comma pi over 2 is what you would get if you flipped these points. And if I include pi 0, 0 pi would put me on the y-axis. I'd get something that's not a function. So I'm going to ignore that one. So I don't want this one. I'm going to go the other way. We have negative pi over 2. Let me use blue there. Comma -1. So flip-flop it. And I get -1. Pi over 2 would be about right here, but on the negative side. So -1 comma negative pi over 2 would be this. So that would be my sine function. And I know it's completed because I've accounted for every possible x value on the domain of -1 to 1. All right, there's no other possible point that I can put in this graph such that it would remain a function. Right, and again, just like with the cosine, you could verify it with the calculator. All right, and then the last one, and the last thing we're going to talk about for tonight, the arc tangent. Again, y equals arc tan of x. So we just learned about the tangent function, so you'd be forgiven if you're not a complete and total instant expert on the topic. But I will just pop in the asymptotes. I'm going to have one at pi over 2. And I would have one at 3 pi over 2, but that's off the grid. So I'm going to go the other way, because pi over 2 and 3 pi over 2 would be separated by 4 boxes. So I'm just going to pop one here at negative pi over 2. And here's negative pi. All right. So I'd have my point right in the middle, increasing throughout the domain. So I could do the same thing over here, but part of it's going to go off the graph. Do the same thing over here, but part of it is going to go off, well, outside the domain anyway. It'll also go off the graph, but this one actually terminates at negative pi and pi because it's a stated restricted domain. All right, so these parts go away, and we have finite points at these locations. All right, so same idea as sine and cosine. I want to grab some points and flip them. Now, the only points that are definite are the ones that are on the x-axis. Everything else I'm just guessing. All right, so here's 0, 0. Let me do that in green. So 0, 0. Actually, I'm going to do it in blue, like I did before. Flip the points, still 0, 0. All right, so that's easy enough. Now, my vertical asymptotes were at pi over 2 and negative pi over 2. So that's going to correspond to horizontal asymptotes at pi over 2 and negative pi over 2. X becomes y and y becomes x. All right. So this is x equals negative pi over 2. And this is x equals pi over 2. So these ones would be y equals pi over 2, y equals negative pi over 2. We have the point in the middle. I just don't have any other points, right? But what I could do is I could look at this and say, all right, I know this isn't 1, 2, all right? And it certainly wouldn't be 1, 2 anyway, because the x-axis isn't in terms of whole numbers. But I can estimate this and say, well, maybe it's pi over 4, comma 2. All right. It actually wouldn't be. It would be 1. But based off the way I drew the graph, it kind of seems like it's a 2. I mean, I guess I could kind of clean it up a little bit, because it really should go through this point here. But you don't really need to know that in order to do what I'm about to do. All right. So we'll say pi over 4, 1, and negative pi over 4, comma negative 1. Flipping. Each one of them get flipped. So 1 comma pi over 4. Again, it's all dependent on the scale. So I'll call this 1, and I'll call this negative 1. So 1 comma pi over 4. Halfway between 0 and pi over 2 would be pi over 4. And negative 1, negative pi over 4. So your graph is going to look something like this. Oops, I made that look too linear. I got to thicken it up. Something like that. If you miss the point, just make the point bigger. All right. So it's gonna have a look like this. Just for whatever reason, I can't really draw right now. I'll give it one last try. Now, one part keeps ending up being too flat. Yeah, that's the best I got, I think. All right. But let me show you what it ought to look like, because it should not be at the mercy of my inability to draw. So arc tangent, oops. Do it again without the oops. So shift tangent, pop in an X, hit OK, take a look at the picture. So it looks like that. And the reason I didn't use any of the points out here is because it would have caused another kind of, I don't want to say like an overlap, because that's not the case. It would cause it to not be a function, all right? Because we would have another part of the graph that would be like up here, and another part that would be like over here. So they'd fail the vertical line test. All right. So that's really it, at least for now. So we just graphed this part sideways. I really can't even, this is brutal. We just graphed this part by flipping the points, and we just graphed this part by flipping the points. All right. These are the parent functions for inverse trig. Right. They're like I showed you on the calculator. You could fairly easily get these graphs right from the calculator. It's not like those more complicated graphs we were doing. So it should be much more manageable. And for this, it's not really that I need you to make the graphs. I just need you to understand the domains and ranges of these graphs so that we can solve trig equations. All right. Well, these are evaluating trig expressions, but we will be solving trig equations as we go forward. All right. So that's the connection. All right. So I am going to stop the recording. I'll leave the